Our next speaker is Professor Chechik from Ilan University and Nvidia. He will talk about images.
Hi there. Oh, great. Oh, it's awesome to be here. Thank you all for coming. I'm going to tell you about an effort, research effort that we've been following in the past kind of 2 years. And this is the problem of communicating about what you perceive, or more formally, we want to develop algorithms and system agents that can communicate with each other and with people about their perceived environment. And do that in natural language, so we can understand when they talk and they don't conspire against us. So if you think about a set of problems around perception and language, like images and text, there are multiple complementing problems. Here's my faithful dog Max. If you present an image, you could train a problem mapping from perception to language. Like you can train a network that try to describe that image, say a sleeping dog. You could also have the other direction. You could have problems mapping from language to perception. And the network you train, given a text, could do a lot of different tasks, like imagine or create images based on this description, or locate that description in a complicated scene or among a large set of distractor images. So I want to tell you about three projects. This is more like a teaser. And if you're interested in the detail, I recommend you go see some of the posters cover some of that work. The first one is about how can we talk or describe images like people do. Okay, so what's this image about? What is this? A dog, right? I mean, everyone says a dog. If you try to be smart, some people say it's a dog with a ball or something. But everyone says a dog. And there's actually a large volume of literature in cognitive psychology from the 70s that studies the way the specific terms that people use to describe objects. Like, no one says animal or carnivore, right? And also, very few people would say golden retriever. And this is in contrast to what happens when you show that to a computer, right? An object recognizer would give you just huge list. I don't know if you can see all of this, but it would tell you a mammal, an animal, and carnivore, and pet, dog breed, even Australian shepherd. So all these labels, they are technically correct for this image, but they're not very interesting. They're not the way that people would describe this image. So the question is, how can we use language that is natural to people? So here's just to explain the problem again. Given an image, you use a pre-trained classifier to create a large set of labels together with their confidence. And the goal is to have a speaker that describes, selects one label or a few labels from this set to describe to a listener. And the assumption of the model is that both share a prior knowledge about the joint distribution of labels for this data set. Now, there's a lot of philosophy and principle in linguistics about this problem. Like, what is a good communication? One of Grice's maxims tells you one tries to be as informative as one possibly can. Another thing tells you should take into account what the listener already knows when you say something. And this seems extremely difficult because it seems like we need to really model the entire human knowledge about images. But it turns out that we can actually do that in some specific settings. So we took a data set called the Open Image data set that has like 150,000 images. And we approximated the joint distribution of labels in this data set. And of course, this is a huge distribution, so you need to approximate it. And we use a directed graphical model called a Chaolu tree. The details are not extremely crucial here, but what's interesting is that once you approximate this distribution, you can count or you can quantify the uncertainty in this distribution. So this tells you how much the listener doesn't know. And you can compute that using the entropy over this distribution. And what you can also do is count how much entropy is left or reduced when you say something. So now you can take every label and count how much entropy it reduces. Now, it turns out it's a bit more tricky because some labels, you have higher confidence than others. Like in this image, it's clearly a dog, but it's hard to tell. Fine-grained labels tend to be, you tend to be less confident about. It's hard to know which kind of dog. So what we actually did was to compute the expected entropy reduction. And now for a given, let's say this nice kitty, for every animal, for every label, you can compute this expected entropy reduction, and you see the system selected correctly the word cat. And what was surprising is that this very principle and like clean measure actually corresponds, has a large, strong agreement with human judgment, almost to the level of inter-rater agreement. And this was tested in like 10,000 images. Two things I want to stress here. This is surprising because this is an unsupervised approach. We never show the system any supervision about what labels people love or not. And also, we did not use the saliency or the visual aspect. This was mostly about modeling the label space. So as a second teaser, so I told you about images to text. I want to tell you about text to images. One thing that people are really good at is, I mean, when we learn, we have two modes. We can learn from examples, but we can also learn from explanations. This is why you have a speaker here explain things to you, right? And we have these two modes, and we still don't have that working very well with machines. One thing you could try to do is to explain, to recognize a visual class just with text. So let me show you that people are really good at that. I can tell you that a jackalope is a rabbit with horns. And you should be able to recognize the jackalope among these four. Can you do that? It should be easy, right? Because it's this guy here. You know what a rabbit is, you know what horns, you can just combine them. And this compositionality is something that people do very easily. So this is a task in a framework called zero-shot learning. And in zero-shot learning, at training time, you actually learn two things. You learn part that learns to recognize the components, like the attributes from an image, like rabbit and horns. And then you also learn another component that allows you to match what you predicted from the image with a description of the class. So you learn these two things. And at test time, you transfer both of them. So you recognize attributes from a new class, an image from a new class, but now someone gives you a description, and you learn to and you use your knowledge about how you do the matching to decide what class it is based on the predicted attributes. So one key observation that Yuval that did this work, he noticed that this matching is actually pretty tricky to do. It seems easy, but it's actually hard to learn a good matching function. And Yuval noticed that often in language, we have kind of a compositional structure that follows kind of a soft and/or logical relations. And this is something very natural. And if you look at Wikipedia, it would tell you that this bird has an olive green wing, a gray-blue head, and a pink feet. So it turns out you can take this and/or logical relation and phrase that as a differentiable model so you can train efficiently. Something that's really hard for networks to do is they get really confused when at test time you present to them either new things or things they already know. And they completely get confused, and some models just always go with the seen ones, some with the unseen ones. And it turns out you can actually write a very clean probabilistic formulation that allows you to combine information from these two modes of understanding, learning from visual samples and learning from explanations. And this led to a very large improvement across all existing baselines in all benchmarks. So I told you about image to text. I told you about text to image. I want to tell you about what happens when you try to do both. In a way, close the loop. If you go back to Max again, if you look at standard image captioning problems, it would tell you something like a sleeping dog. This is a nice caption, but if you have a lot of images that have a lot of other dogs, this would not be useful. What you want is something that's much more selective and discriminative that allows you perhaps to recognize that specific image in that set. So you want something like a white-bellied dog sleeping on a blue pillow. So how can you do that? It's really hard to create a large training set for that. Well, you can build an adaptive loss using another network, a listener network. And you can aim to train both of them jointly with a goal that the listener network tries to find the correct image in this distractor set. So you can build some discriminability loss using ranking loss, and just push gradient all the way through. So one problem, this really doesn't work, because when these two agents start to talk with each other, their language just drifts away, and they start to speak in secret language. We discovered that you can actually constrain them to speak in natural language we can understand if you just add naturalness loss that makes sure they're not too far from natural captions of those images. Now this still, now you just balance these two losses. Now this still really doesn't work because it's really hard to optimize through a language layer. It is discrete, it is stochastic, and there are a lot of suggested algorithms to do this optimization. Here we took advantage of the following fact that these two agents, they're actually cooperative. They try to help each other to achieve the same task. And it turns out that in a cooperative setting, this is much easier than GANs or adversarial settings. In cooperative setting, the speaker can pass more information, and in our case, it passed continuous distributions over words instead of just single words. And this really helped optimization, both it was faster and achieved better results. I'm showing you some results here. This is a trade-off between discriminability, how useful the caption is, and naturalness, how English-like it is. And you can look at all the trade-off curve between them. And this is a baseline model that was frozen, not trained jointly. If you train jointly, all the previous methods give you a nice boost, and if you add this new method, you get a total of like 50% boost of discriminability with the same naturalness, which is huge here. So I told you about 3 projects. One is how to speak more naturally, like a person with using an unsupervised approach. How to learn without samples, just explain to your computer what you want to do. And also how we can teach agents to speak with each other in natural language so we can understand. So, and also that we can communicate in an environment where you have agent and systems. So I want to conclude by saying that this field of combined vision and language, it's very interesting algorithmically because it requires you to combine these 2 modes of programming, if you wish. This differential programming, deep networks, learn from examples, and symbolic reasoning, which we are used to. And this would become even more and more interesting as we move to perception that is embedded in an agent. More details are at the posters and at our lab website. Thank you so much. If you have a question, wait for the microphone. There's a question there.
While we wait for questions, maybe those on the back, please, there are many seats available here. Nobody heard what I said.
Everyone in the back, you're invited to sit in front. There are plenty of empty seats with comfy cushions. Okay. Thank you all.
Thank you again.